In this chapter, it starts out with this quote from Damian Conway: "Documentation is a love letter that you write to your future self." For me and for everybody else, documentation is an act of care. By documenting your work, you're showing consideration for your future self and for others who might need to understand or build upon what you've already done. And it's kind of like in this example that Damien says, it's like a love letter that's expressing affection and consideration for the recipient. Documentation is a gesture of care towards your future self when you might need to revisit or understand your work. It's that tool for the future understanding. Documentation captures that crucial information and context about the project or the process that you're working on, and helps your future self or others that work on the project in the future so that they can build on your work without having to retrace your steps or struggle to figure out what you did and why. And so that's a really big investment in efficiency and effectiveness, because taking that time to document your work saves future you and future others from having to do guesswork and try to backwards engineer decisions. And this helps facilitate comprehension and continuity in the future on that project. Section 1, let's start with the uses and audiences for architecture documentation. We have a few different purposes with what we use documentation for. It should be sufficiently transparent and accessible to be quickly understood by new hires. So if someone joins your team, this documentation is going to be how they get up to speed quickly on your application or your software system, whatever you've got. It should also be sufficiently concrete, solid enough to serve as a blueprint for construction or forensics, looking back at an incident and figuring out what happened. And it should also have enough info to serve as a basis for analysis. Some audiences are going to see documentation as prescriptive, which means it's going to be what should be true. This is putting constraints on what has yet to be made. Like, for example, the developers who are building the system, what is prescribed? What do we need? What should be built and how should it be built? It's constraining and prescribing what the app will look like. And for other audiences, it's going to describe what is true. This recounts the decisions that we've made about the design system, or about the system design, about patterns, things like that. So it's describing things. So it can be both prescriptive to describe what should be true and descriptive to describe what is true. There are four primary uses for architecture documentation. Number one, it's a means of education. Two, it's a primary vehicle for communication among stakeholders. Three, it serves as a basis for system analysis and construction. And four, it serves as the basis for forensics when an incident occurs. Let's start with the means of education. This is how we introduce people to the system. This could be a new team member. It could be an external analyst who is going to dig into some features or something about the system. It could be a new architect. In many cases, the new person is even just the customer who you're showing your solution to for the first time, maybe for funding or to get the go-ahead approval. Number two, communicating among stakeholders. Its precise use as a communication vehicle depends on which stakeholders are doing the communicating. If it's the future architect, this could be you, the original architect, or it could be a replacement. Either way, you're guaranteed to have an enormous stake in the documentation. A new architect is going to be interested in learning how the predecessors tackled the difficult issues in the system. They're going to be interested in why particular decisions were made. And even if it is the same person, if the future architect is the same person as who originally designed the system, the documentation is a repository of their thought. It's a storehouse of those design decisions that are too numerous and too intertwined to be able to be just remembered. There's more stakeholders that are involved, and we'll look more at those in section 22.8. Third, the system analysis and construction. The architecture tells implementers, those developers, which modules to implement and how those modules are wired together. These dependencies determine the other teams with which the development team is going to need to communicate with, if there's other resources or systems they're going to interact with. And for those interested in the design's ability to meet the system quality objectives, the architecture documentation is used for evaluation. So it's going to need to contain necessary info to evaluate a variety of attributes like the security and the performance, usability, availability, modifiability, those quality attributes that we talked about earlier. And then finally, the basis for forensics. When an incident occurs, somebody is going to be responsible to track down the immediate cause for the incident and the underlying cause. Information about the flow of control immediately prior to the incident will provide the as executed architecture. For example, a database of interface specs will provide context for the flow of control, and component descriptions will indicate what should have happened in each component on the trace of events. Regardless of everything going on with the documentation, one of the most important parts is to keep it up to date. And this is actually really, really hard with a project, either because of time constraints and developers are just trying to keep things moving and there isn't time to document, or changes are happening too fast, or it's just forgotten. So here's a few different strategies I'll just mention real quick. One is you should try to establish some documentation standards. What are the guidelines for the architecture documentation? So what format, what tools, how detailed should it be, what conventions? If your developers are the ones that need to update the documentation, you're probably going to need to have a limited level of details because they're not going to want to spend a lot of time on it. If you have the architect that is, the one keeping it up to date, you might be able to get a deeper level of details. You'll want to figure out how you're going to integrate your documentation into your development workflow. It should be a part of your development process because, as you'll see as we get into this chapter, it's really important to have up-to-date documentation, and it really helps to understand what's going on and keep track of those decisions. If you can, automate the documentation generation. So there's tools and frameworks that can be used that will help generate documentation. This could be tools like Swagger, for example, which generates API documentation. There's a lot of different options out there, so see if there's an option that works for your project. You might want to schedule regular reviews where you're going through the documentation and updating it. You might want to assign ownership. You could document incremental changes rather than waiting until there's a big update. Providing training and support if there are a specific set of people that need to update the documents. Make sure they know what they're doing. And also consider using version control. That's really helpful to use version control to allow for tracking of the changes, allowing reviews and reverting if you need to, just like when you change the code. Let's talk about notations. Notations for documenting views can differ considerably in their degree of formality, and that's what we'll focus on here in this section. There's 3 different formalities that we'll talk about: informal notations, semi-formal notations, and formal notations. Informal notations are views that are usually depicted graphically. They use general purpose diagramming and editing tools. Visual conventions are chosen for the system at hand. It's usually just box and line drawings. You've probably seen stuff like this. It could be a PowerPoint where you're just kind of sketching some things out with the boxes and lines, a similar app. It could even be hand-drawn sketches on the whiteboard. The semantics of the descriptions in informal notations are in natural language. They can't be formally analyzed. And these types of notations are easier to create than formal notations, but they're going to provide fewer guarantees because they're not something you can really use for analysis. Semi-formal notations are views that might be expressed in a standardized notation that prescribes graphical elements and rules of construction, but doesn't provide a complete semantic treatment of the meaning of those elements. So a rudimentary analysis could be applied to determine if a description satisfies certain syntactic properties, UML is probably something you've heard of and seen before, and that's a semi-formal notation in this sense. Most widely used commercially available modeling tools use notations in this category. Formal notations are views that may be described in a notation that has a precise, often mathematically based, semantic. Formal analysis of both syntax and semantics is possible, and a variety of formal notations for software architecture are available. Generally referred to as architecture description languages, or ADLs, these typically provide both a graphical vocabulary and an underlying semantics for architecture representation. The usefulness in ADLs is in their ability to support automation through associated tools. Automation can provide useful analysis of the architecture or can help with code generation. However, in practice, the use of formal notation is really rare. These typically take a lot more time and effort to create and understand, but the effort is repaid with reduced ambiguity and more opportunities for analysis. So there's definitely trade-offs with formal notations, but you do get a lot of good benefits from it. Views. One of the more important concepts associated with architecture documentation is the view, and this is something we've talked about in earlier chapters too. But remember that software architecture can't really be described in a single dimension. A view represents a set of system elements and relations among them, but not all of the system elements, just those of a particular type, and gives us just that picture from that angle and perspective that we're looking at. Documenting an architecture is a matter of documenting the relevant views and then adding documentation that applies to more than one view. So what are the relevant views? That depends on your goals. Depending on what you want out of a view, that's going to impact what kind of a view is relevant for you. Different views can expose different quality attributes to different degrees. For example, a module view would let you reason about your system's maintainability. A deployment view would let you reason about your system's performance reliability. So what quality attributes you're concerned about and your stakeholders are concerned about will affect which ones you choose to document. It just depends on what your needs are. In this section, we'll talk briefly about 4 different categories of structure-based views. Most of these were introduced in Chapter 1. If you want more details than what we cover in this talk, you can dig into it in Chapter 22 and Section 3. Let's look at module views. First, we have the elements. The elements in a module view are the modules, which are the implementation units of software that provide a coherent set of responsibilities. The relations among those elements, there's a few different ones. There's is part of, which defines the part or whole relationship between a submodule, which is the part, and the aggregate module, which is the whole. There's the depends on relationship, which defines a dependency relationship between two modules. There's the is a relationship, which defines a generalization or specialization relationship between a more specific module, like the child, and a more general module, the parent. So those are a couple of relations. Constraints, limitations, if you will. Different module views could impose topological constraints, like limitations on the visibility between modules. What are module views good for? They are great for a blueprint for the construction of the code for your developers. They're great for analyzing the impact that a change will have on the code, making plans for incremental development. They're great for requirements for the traceability analysis. They're great for communicating functionality of a system and the structure of its code base. Also great, it's great for a lot of things. It's great for supporting the definition of the work assignments, implementation schedules, and budget info. So that's, the actual logistics of getting the work done and building the thing. These views are also really helpful for showing data model. The component and connector views, remember those are also called the CNC views. The elements in these type of views are the components, which are the principal processing units and the data stores, and the connectors, which are the pathways of interaction between components. This is kind of like elements and relationships, but we have the components and the connectors in this case. The relations are going to be called attachments. These are the components that are associated with connectors, and that gives you a graph. The constraints are that components can only be attached to connectors, and connectors can only be attached to components. You can't have a single connector floating around. It has to be on a component, and you can only have attachments built from compatible components and connectors. What do we use it for? Mainly to show how the system works. It's going to help guide development by telling us the structure and behavior of runtime elements, and it's also going to help us reason about the runtime system quality attributes like performance and availability. What are the notations? Again, box and line drawings. Each component type should get a symbol, and each connector type should get a symbol, and then list that in a key. So UML components are really good semantic matches for drawing these CNC views. Allocation views. The elements for an allocation view are the software element and the environmental element. A software element has the properties that are required from the environment, and the environmental element has the properties that are provided to the software. The relations are allocated to, so a software element is mapped or allocated to an environmental element. Constraints, this is going to vary depending on the view. Usage, this is really good for reasoning about a lot of different things. It's going to be helpful for thinking about performance, availability, security, safety. It's going to be helpful for thinking about distributed development and how you want to spread out the work between teams. It's going to be helpful for concurrent access to the software versions. It's going to be helpful for the form and mechanisms of system installation. So a lot of different reasons you might want to use this view. All right, last one. This is a new one. This is quality views. Quality views are formed by extracting the relevant pieces of structural views and then packaging them together. So these are 5 examples. There's a security view, communications view, exception or error handling view, reliability view, and performance view. Security view, this is going to show all the architectural measures taken that provide security. Things like components that have some sort of security role or responsibility, how those components communicate, the data repositories for security information, repositories that are of security interest, what kind of security measures are there, like physical security, what operation of security protocols and where and how humans interact, and how the system responds to specific threats and vulnerabilities. Communications view might be especially helpful for systems that are globally dispersed and large and diverse. These would show all the component-to-component channels, various network channels, quality of service parameter values, areas where there's concurrency. It could be used to analyze certain kinds of performance and reliability, like a deadlock or race condition. It could also show, for example, how network bandwidth is dynamically allocated. Exception and error handling views could help illuminate and draw attention to error reporting and resolution mechanisms. So it could show how components detect, report, or resolve faults or errors. It could help an architect identify sources of errors and specify what corrective actions need to be taken. It could also help facilitate those root cause analyses in those types of cases. Reliability views would model reliability mechanisms like a replication and a switchover. It could also depict timing issues and transaction integrity. And finally, performance view. This would include those aspects of the architecture useful for inferring a system's performance. That might show things like network traffic models, maximum latencies for operations, etc., etc. With all of those different views, we have to also think about combining views, because all structures in an architecture are part of the same architecture and they exist to achieve a common purpose. And because of that, and because they're all part of that same system, they have strong associations with each other. So managing how architectural structures are associated is another important part of what the architect's job is, which is independent of whether or not you document any of those structures in the first place. Sometimes the most convenient way to show a strong association between two views is to collapse them into a single combined view. And the combined view can contain elements and relations that come from two or more other views. One of the things to watch out for, though, as we dig into this, is to make sure you don't overload your views with too many mappings. There are a lot of naturally occurring view combinations. For example, CNC views often can be combined together. Separate CNC views tend to show different parts of the system or show decomposition refinements of the components in other views, and often a set of views can be really easily combined. You could also combine deployment views with any CNC view that shows those processes. Processes are the components that are deployed into processors, virtual machines, or containers. And there's a strong association between the elements in these types of views. We also have decomposition views and any work assignment, implementation, uses, or layered views. Those could be combined. The decomposed modules form the units of the work or the units of development and uses, and those modules can populate different layers. This is an example of what a combined view might look like. This is an overlay of a client server, multi-tier, and deployment view. So you can see some of the details there where they've combined several layers of information so that you can get the context and understanding and a fuller picture than what you would have gotten as if those were just separate. All right, behavior. How do we document behavior? There's a couple of different notations that we want to make note of for documenting behavior specifically. There's the trace-oriented notation and then comprehensive notation. Trace-oriented, there are 4 notations for documenting traces. And traces are sequences of activities or interactions that describe the system's response to a specific stimulus when the system is in a specific state. So a trace describes a sequence of activities or interactions between structural elements of the system. The 4 notations that we're going to talk about are use cases, sequence diagrams, communication diagrams, and activity diagrams. There's other notations out there like message sequence charts, timing diagrams, etc., etc. We're just going to focus on these 4. So first, let's talk about use cases. That describes how actors can use a system to accomplish their goals. So for this, a UML use case diagram is a good way to provide an overview of the actors and the behavior of the system. And an actor is something that causes an action, and then what happens from that. A UML sequence diagram shows a sequence of interactions between instances of elements from the structural documentation, and this is helpful when designing a system for identifying where interfaces need to be defined. Let's look at an example of the sequence diagrams. That's our second example. This has 2 different dimensions. The vertical is time, and the horizontal is the various instances. So vertical, we're looking at here, this is the beginning of our timeline up at the top, and as time goes on, we move down. So you can see that we start up at the top, and as time progresses, you can see I'm moving down vertically. And then moving across, again, is the different instances. So we have a login page, a login controller, the user direct access object. So you can see how we move through the instances, and as time passes, we move down the timeline. It's important to note that sequence diagrams are not explicit about showing concurrency, but if that's your goal, you should consider using activity diagrams instead. Okay, the third example in this case is the communication diagram. That's going to show a graph of interacting elements and annotates each of the interactions with a number denoting its order. So that's useful when the task is to verify that an architecture can fulfill the functional requirements, but it's not useful when you're trying to understand the concurrent actions and what's important, like conducting a performance analysis. An activity diagram is similar to a flow chart. That's going to show the business process as a sequence of steps called actions, and it's going to include notation to express the conditional branching and the concurrency, as well as showing the sending and receiving events. It does not show the actual operations being performed on specific objects, which you would use the sequencing and communication diagrams for. It is useful to broadly describe the steps in a specific workflow. So an example of an activity diagram would be this from figure 22.3. And you can see the conditional branching with the diamond symbols. Conditional branching meaning a decision is made. So is it, in this case, underwater or not underwater? So that's what those diamonds mean. And then you're going to flow through the diagram and be able to see multiple traces from the system. Activity diagrams usually don't attempt to show all possible traces or the complete behavior of the system, but it gives you a good idea. Comprehensive notations show the complete behavior of structural elements. Given this type of documentation, you can infer all possible paths from the initial state to the final state. And state machines are a kind of formalism used by many comprehensive notations. This is a state machine example from figure 22.4, and that shows the states of a car stereo. So each transition in a state machine diagram is labeled with the event causing the transition, and the transitions correspond, in this example, they correspond to the buttons the driver can press or driving actions that affect the cruise control system. These transitions can also specify a guard condition, which would be enclosed in brackets. So, for example, the CD button, the guard condition is if there's no CD in the player. And transitions can also have consequences, which are called actions or effects, which are indicated by a slash. So, like the eject button here is going to have the action eject disk. In addition to the views and behavior, comprehensive information about architecture is also going to include mapping between views, documenting patterns, context diagrams, variability guides, rationale, glossaries, acronym lists, document control information. There's a lot that goes in the documentation. So let's cover some of that. Because all views of an architecture describe the same system, it stands to reason that any two views will have things in common. Combining views, like we did in section 22.4, can produce a set of views. And associations between elements across views are, in general, many to many. For instance, each module may map to multiple runtime elements, and each runtime element may map to multiple modules. View-to-view associations can be captured as tables. This is just a simple way to document it. You can do this by listing out the elements in the first view in some convenient lookup order, and then the table itself should be annotated or introduced with an explanation of the association it depicts. An example would be is implemented by for mapping from a CNC view to a module view, or implements for mapping from a module view to a CNC view, or included in for mapping from decomposition view to a layered view. There's a lot of different ways you can go about that, but a table might be a simple way to document that. Documenting patterns. So if you use patterns, you really need to document those in your documentation. So first, you need to record the fact that a given pattern is being used, and then you should explain why this solution approach was chosen, why that pattern is appropriate for the problem that you're solving, the problem at hand. Context diagrams show how the system or portion of the system relates to its environment and depicts the scope of the view. Context means an environment with which the part of the system is interacting, and those entities could be humans or other computer systems. It could be physical objects like sensors, etc. Variability guides just show how to exercise any variation points that are part of the architecture that's being shown in that view. Rationale is explaining why the design reflected in the view came to be. The goal of this section is to explain why the design has its present form and also provides a convincing argument for why it came to be. So there's more details about this in section 22.7. Glossary and acronym list. So architectures contain a lot of specialized terms and acronyms, and your readers need to figure out how to decode these somehow. So having a glossary and an acronym list makes sure that all of your stakeholders are speaking the same language, so to speak. Document control information is usually captured in the front matter, and change control tools can provide a lot of this information. This is going to be things like the issuing organization, the version number, date of issue, status, change history, what the procedure is for change requests, stuff like that. All right, documenting the rationale. We talked about that just a tiny bit in the last section, but when you're designing, you're making really important design decisions, and those decisions are to help you achieve the goals of each iteration. So whether those are quality attributes you're trying to meet or functional goals, whatever your goals are, you have a reason for making the decisions that you make. So design decisions should include things like selecting a design concept from a few different alternatives. It should include creating structures by instantiating the selected design concept. You should be establishing relationships between elements and defining the interfaces. You should be allocating resources like the people, the hardware, the computations. Diagrams don't always show why decisions were made to achieve a result. So recording decisions beyond the representation of the chosen elements and relationships and properties is really fundamental to help in understanding how you arrived at a result. These are a few examples with the rationale in italics here. So an example would be something you did to introduce concurrency, and the rationale being that you introduced it to be able to receive and process several events simultaneously. Or another example of a decision is to implement the messaging pattern, and the rationale would be that it imposes a performance penalty. So you're explaining that there is a negative connotation to this decision, you've acknowledged that, but it was chosen because some implementations have higher performance and will be helpful to support quality attribute scenario QA3. So this is just a made-up scenario in this example, but if you have documented quality attribute scenarios, you can refer back to those and say, this is why we chose this, made this decision is to support that scenario that was required. Other things that you might want to think about and ask as you're considering rationale: what is the evidence that was produced to justify that decision? Who did what? Were there shortcuts taken and why? What trade-offs did you make? What assumptions did you make? Think about those things as you're writing up your rationale for your decisions. As an architect, one of your primary obligations is to identify the real stakeholders for your project. And that also involves identifying how you're going to document things so that it can be used by those different stakeholders. We've got a lot of different stakeholders here. We have project managers. We mentioned earlier that certain views like module views, allocation views, context diagrams, these types of things can help with scheduling and resource assignments and contingency plans, and that's the type of stuff that a project manager is going to care about. So designing views that are useful for them is really important for the logistics of getting the project done. You have the development team who are actually implementing the software system. They need to have constraints for how to do their job. They'll want to have an idea behind the system, where should the functionality be implemented, what are the details of the assigned element that they're working on, what are the interfaces for that element, are there certain code assets that they can utilize, and the types of views that might be most useful for them could be module views, the CNC views, allocation views, system overviews, context diagrams, things like that. You'll see a lot of times the module views and CNC views and allocation views, they come up a lot for stakeholders, so those are really useful views. Testers and integrators need access to the interface documentation. They need to have behavior specs and uses views. Again, module views, component and connector views, allocation views, context diagrams for the modules that they're testing or integrating, any interface documentation, any behavior specs. Those are all things that testers and integrators care about. We could keep going and digging into all the different views and details for each stakeholder here, but you can read about that more in the chapter. But do remember that future architects have a vested interest in everything architect related for this project. So it could be you after a period of time, or maybe your replacement once you're promoted and assigned to a more complex project. You'll want to know, or they'll want to know, all of the key design decisions and why they were made. You shouldn't expect yourself to remember why a decision was made 6 months to a year to 3 years down the road. Document that stuff, and that way if you've moved off the project, somebody else can have some background information without having to do guesswork. We've talked a lot about the contents in your documentation, but there are issues with dealing with how the documentation is formed, how it's distributed, and how it can evolve over time. There are some different practical considerations we can talk about. Modeling tools. There are a lot of commercially available modeling tools, and many of those tools can offer features that are aimed at practical, large-scale use in industrial settings. That really needs to be evaluated, the cost of the tool against what it would cost the project to achieve those capabilities on its own. Like I said, most of those tools are aimed at large-scale uses in industrial settings. So for smaller projects, those tools may not make a lot of sense. You should also consider online documentation, hypertext, wikis. This is the most common. I've seen wikis and documentation even within version control repositories like GitHub. And documentation for a system can be structured like linked web pages. And tools like wikis allow you to create those shared documents where a lot of stakeholders can contribute. However, you do want to be mindful about who can make changes. There are a limited set of people that can make changes, like the architect can make changes, but maybe other stakeholders can comment and add clarifying information. Who is allowed to change what? And then setting appropriate user controls. You can also follow a release strategy. You should specify the process for keeping important documentation current. Remember, that's one of the hardest parts, is keeping documents current. And you need to document artifacts. And document artifacts should be subject to version control. Just like your code has version control, your documents also should, so that you can revert or see when things were changed and how they were changed. Documenting architectures that change dynamically. This is a little bit more interesting and complicated, because dynamic architectures change faster than the documentation cycle, usually. No one wants to hold things up for new architecture docs. They're not going to wait on a release when something is very dynamic. So what you can do is document what is true about all versions of your system, and document the ways the architecture is allowed to change, and then generate interface documentation automatically as best as you can. Traceability is really useful for linking your specific design decisions to specific requirements or specific business goals that led to them. So remember, in our earlier example, we had a fake quality attribute scenario, and in our rationale for making a decision, we specifically mentioned that scenario. So that type of traceability is useful for making those connections for why decisions were made and why we're using certain patterns or certain decisions. All ASRs should be covered in the architecture's trace links, and this could be represented informally in a table, or it could be something that's supported in the project's tool environment. All right, that was a huge chapter, but let's just do a quick summary of everything that we covered. Writing architectural documentation is a lot like other types of writing, where your golden rule is you need to know your reader. Who is your stakeholder? Who is your audience? That's what you're drawing your views for and what you're documenting for, is how will this be used? What is it necessary for? Architectural documentation is a means for communication. It can communicate up the management chain, down to developers, across to peers. It's that communication vessel for you. Architecture is a complicated artifact, and it's best expressed by focusing on particular perspectives called views. You choose the views that you need to document based on what the needs are. You choose the notation to document those views in, and that may involve combining various views that have a large overlap. And you should document structure, but also behavior. Also, you should document the relations among the views in your document. You should document patterns you use, the system's context, variability mechanisms built into the architecture, rationale for your design decisions. There are other practical considerations for creating, maintaining, and distributing your documentation, like choosing a release strategy, or choosing a tool like a wiki, or creating documentation for architectures that change dynamically. With that summary, that concludes our chapter on architecture documentation. Thanks for your time.